Okay, thanks. All right, let's go. It's a great honor to be lecturing to the survivors of these 2 weeks. I'm very proud of you that you all made it out. And so, as a thank you, we're going to prove the get in all its glorious detail. No, we're not. But okay, just maybe to recap from last Wednesday. So, what we set out to do was to say, okay, what happens when you train these two-layer networks that we've come to love so much in our teacher-student setup? What happens if we train these on inputs that have more structured? And in particular here, the way we implemented structure in our data set was to say that, okay, we're going to train these networks on the outputs of pre-trained generative models, right? So just as a quick reminder, our model looked like this. We had a latent vector C. This is just an IID random variable. And then the input was given by some generator. And at the end of last lecture, you remember I showed you, convolutional GANs and normalizing flow and all these things that also Max Welling discussed last week. So this is really just some complicated nonlinear function that gives you the inputs. And then the true labels for these are obtained from a teacher neural network, which is a two-layer neural net with M hidden nodes and looks a little bit like that. Up. And crucially, this teacher network is acting on the latent variables. Okay, so the things I put into the generator. And then I'm trying to learn this function x to y with another two-layer neural network. That's the student. And the student as parameters theta, it's acting on x. Okay, so it's living in a different space from its teacher. And we wrote its output like this. Okay. And then, okay, we thought about this. So the goal was to be able to say something about this setup, in this setup, analytically, or at least with some of the tools that we've learned this week. And so last lecture was about these two guys, okay, these local fields or pre-activation, so the thing that you feed into the nonlinearity in your hidden layer, okay, and I tried to convince you that these are actually the important variables if you want to do online learning, if you do a replica calculation. Those are the guys that will show up in your delta functions. And so what you really want to, if you want to do an analysis, is you really want these guys to be Gaussian, okay? And sort of the bottom line of the get, of the Gaussian equivalence theorem, is that it turns out that rigorously for single-layer generators, but also empirically, for a much larger class of generators, these two guys are in fact Gaussian. Okay, and the condition for this was that the weights of the students shouldn't align too much with the dominant directions of the covariance of the inputs, right? And in practice, this doesn't seem to happen. Okay. Now the goal for today is to put this insight to use. Okay, and so the goal for today will be to use this Gaussian equivalence theorem to say something about the dynamics of these two-layer neural networks. Okay, and so to really make use of what we learned on Wednesday. And in particular, we are going to look at a certain limit for stochastic gradient descent in which the dynamics of such a student can be described by ODEs. Okay, this is this famous ODE limit that was solved and written down by Biel and Riegler and Saad and Sol in the 90s for IID students, so for IID inputs. And so we're going to start with that, and then we're going to see how that translates to this model. And on the way, we're also going to try to look a little bit how this compares to other ways of looking at the dynamics, notably the mean field limit, where here we're in a limit where we make the input size very big. Okay, so that's our thermodynamic dimension. But you can also make the hidden layer of the neural network very big, right? And then you get slightly different dynamics, at least on the formal level, but we'll find some of the phenomenology actually appears in both cases, and okay, that's something we're just going to try to keep in the back of our heads for today, okay? All right. Let's see, okay. So what are actually the dynamics that we will try to understand, okay? They're really simple. We're just going to focus on stochastic gradient descent. So in other words, if I write this a bit in a formal way, the parameters theta of your student at the mu step, they're just given by a simple weight update like this. Okay. Okay, so E is some energy or some loss function. Here we're going to focus on regression tasks, so this is just going to be a quadratic cost function. And the idea of stochastic gradient descent is, of course, that I'm only using one, a mini batch of samples to evaluate this gradient rather than the whole training set that I might have. Okay, and in particular, we're going to look at sort of two limits here. We're going to look at this in a limit where, first of all, I have lots of data. In fact, I have so much data that at each step of my SGD, I can use a new sample from my data distribution, and I'll evaluate the gradient with that new sample. Okay, so that's called also the online learning limit, and that's something that has been studied a lot. It simplifies things in the sense that sample complexity is now taken out of the picture. Right? There's this whole host of questions around, how much data points do I actually need to learn a certain function? Okay, or to learn a certain function to within a certain approximation error. And so there's a whole host of questions around that. Here you have as much data as you want. So sample complexity is not going to hurt you. And in a sense that will simplify things technically. It also simplifies things a little bit conceptually, because it means that now we can really focus on what the algorithm does, right? So now we can really ask questions about how well does SGD do in sort of the best possible conditions, right? And then sort of the second limit, if you want, although that's slightly less important, is we're going to look at the limit of mini batch size 1. So we're really just using one sample at each step to evaluate the gradient. Okay? Okay, let's write down these equations a bit more in detail. Okay, so the updates for the first layer will, for a quadratic loss, and this type of neural network looks something like this. All right. Exactly. And then we also have the updates for the second layer. And they will look something like this. And delta is just the error of a student compared to the teacher for the particular input you're using at this move step. Okay, so this is just going to be something like, actually let's just write like this. Okay. Okay, nothing fancy here. The one slightly, maybe non-trivial modification to this that we're going to do, this is really what you get if you just evaluate the gradient. Okay, so in particular, this square root of n pops out because of the way that we normalize this pre-activation to make sure that it's order 1. Okay. Now, the second thing we're going to do is we're going to rescale the learning rate for the second layer weight a little bit, and we're going to rescale it by n. Okay. This is really a little bit for mathematical convenience. You could also use the same eta here in both cases if you just simulated this. But you make it for mathematical convenience because if you rescale the learning rate here like this, we'll later see that there's a well-defined limit where the dynamics of these guys are described by ODEs. Okay? And if you want the sort of, on a conceptual level, the way to think about this, or the way I think about this, is that as you do one step of gradient descent, right? Here you're changing in the first layer order n variables. Right, so you're making lots of small changes to all these variables, so that results then in some sizable changes on the output. And here you only have order 1 variables in the second layer. Okay, and so sort of to stabilize your dynamics and to make sure that these guys don't fluctuate like crazy, you rescale the learning rate here. And later you'll see that mathematically this is also what makes the most sense. And if you don't like that argument, then just rescale it and follow. That's it. Okay, so these are the dynamics, and now of course people have looked at this in sort of many different ways, right? Many different lines of attack. So you could, for example, look at the case where the networks are linear. So where the G is just, G of lambda is just lambda. That has the advantage of being that you can do this even for deeper neural networks. Okay, and this is a line of research that has been really explored by Andrew Sachs and the group of Surya Ganguly. And you know, this is a reference from 2014, and then again Advani and Sachs in 2017, who looked at this, and from which we learned quite a lot, even in the linear case. Because the interesting case, or the interesting thing, if you make the network linear, is that okay, the network it's linear, so it's just a matrix multiplication, but the dynamics of the weights are nonlinear. Okay, and so a lot of the interesting effects that arise in these linear networks, they are due to the fact that the dynamics of the weights will be nonlinear. Okay. Another really interesting way to attack this, if you want to not use this assumption of lots of data, okay, if you want to look at this for a fixed data set, is the Dmft approach that you know, was covered in Pier Francesco's lecture and in Francesca's recent work and her talk. So that's another really intriguing technique, because if you have a finite data set, you now have training error and generalization error, which are different, right? Here in this case, and so you can think about things like the generalization gap and all these things, right? Here in this approach, because you have so much data, and you're using a new sample at every time, your generalization error, it's basically your training error, right? There's only one type of error. So we can analyze this in detail, but we cannot, for example, look at something like the generalization gap, because this model just doesn't have one. You're basically doing gradient descent on the generalization error rather than the training error. Okay? And maybe as a last limit that I'd like to mention, where you can also say a lot about the dynamics, is a somewhat complementary limit where you send the hidden layers to infinity and you then approximate the whole network as a Gaussian process. Okay? So this is an idea that goes back to the 90s. Redford Neal first had this idea, I think, in his PhD thesis, so pretty good. And recently people have sort of picked that up again, extended this. There's quite a lot of work coming out of Google Brain these days using these techniques, and they can be really instructive too. Okay? But we're going to focus on this online learning limit with this scaling, and now we're going to try to find some ODEs to describe the generalization error. Okay, that's the goal here. Are there any questions so far? Good. Okay. So, even though we want to look at the dynamics, let's start with the statics of this model. Okay, and when I say the statics of this model, what I mean is let's think a little bit about how can we express the generalization error in this model. Okay, so the generalization error is something we've all seen and know very well by now. Up. And if I expand this, so the average here is taken over the C's. So this is sort of a static question, because now I'm asking what's the generalization error for a given student and a given teacher, okay, with these two sets of weights. So nothing is moving. I just give you two networks, and I want to know how well is one doing with respect to the other. Okay? Now this is a bit of a tedious quantity, right? Because it has some high-dimensional averages in here, but we can do the usual statistical physics trick, and we can rewrite this in terms of order parameters. Okay? And they appear quite naturally if you write this out. So you have the student here. You have the teacher. Actually, let's expand the square too. Okay? So what you'll then have is a term like this, a term for the teacher, and a mixed term. Right, this is what we did on Wednesday, and this is what convinced us that it makes sense to look at these lambdas and these nus, okay? And now, on Wednesday, we found that, okay, we can actually fairly safely assume that these guys are Gaussian. Now, why is that really useful here? That means that, we're of course smart, and we have centered our inputs, so the mean of them is 0. So in other words, the mean of lambda k and the mean of the nu n's will be 0. So the whole distribution of lambdas and nus, over which we have to distribute now, can be encoded in the second moments of the distribution. Okay, and so the second moments, we will call them Q and R, and we will talk a little bit in a second about sort of what's their the physical interpretation, or what they mean for the learning process. We will have also the static covariance of the teacher fields. And okay, we have the second layer weights. And because they encode the whole distribution of the lambdas and the nus, you can rewrite basically the generalization error as a function of just these order parameters. Okay, and that's very nice because now you've turned this quantity which depended on some high-dimensional variables and that included some high-dimensional averages into a quantity that can be written in terms of order 1 quantities, right? And that's the whole point of statistical physics. And so now, if we want to analyze sort of any learning problem, right, the goal becomes, okay, we have to understand how these guys evolve, okay? And to sort of get a better feeling of what these guys mean in terms of physics or in terms of physical intuition and how these guys evolve, let's look at a simple case to warm up. Let's look at the classic case of Sadensola and Biel and Riegler, and let's look at what these guys look like when I'm training on IID inputs and a teacher that's acting on the inputs directly. Okay, so this is the vanilla teacher-student setup, if you will. Okay, so vanilla teacher-student setup. So like I said, this is seminal work by Sadensola in 95 and Biel and Riegler also in 95. Who looked at this. So now, just as a reminder, our X are just nice and Gaussian, and our teachers are acting on the inputs directly. Okay. Now let's pick one of these covariances. Let's pick, for example, R. Okay, RKM. So that's the covariance of the teacher and the student local fields. And if we just plug in the definition of these guys, we'll find something like this. Okay, and now of course, because the inputs are IID Gaussian, this simplifies very much, and it just becomes the dot product between the weight vector of the Cave student node and the Mth teacher node. Okay. This is of course, this is nice because they're not living in the same vector space, so I can actually dot them. There's no problem. And similarly, I can do the same calculation, for example, for the student-student overlap, okay, for the covariance between the lambdas. And I guess you'll all believe me when I tell you that this is just going to be the dot product between the student node weight vectors, okay? And then similarly for the teacher, okay? Now let's say, for example, that I drew my teacher weight vectors IID at random, okay? In this case, this teacher overlap matrix will just be the identity matrix, okay, at least in this high dimension limit. And then we can look a little bit at the generalization error and see how, see how we can interpret them and what they tell us about learning, okay? So basically, if you have orthogonal teacher vectors, right, what you want to do is you want to recover your teacher vectors, right? Remember, this is the case where the teacher and the student basically have the same architecture, okay? And so, in other words, this R overlap vector, it's going to tell us how well is the student doing at recovering the teacher vector. And we're going to measure that by the angle between these two vectors, okay? So the hope would be that initially these two guys will be orthogonal on each other, right? Because they're going to be a random vector in the teacher that I drew and the random initialization of my student that I also drew from, IID. So with very high probability, they're going to be orthogonal to each other. This guy will be 0. And then I hope that as I learn, I'm picking up something about the student, and these two vectors will align. And so their angle will decrease, and this overlap parameter will go up. And we'll see a little bit later that this is basically what's happening. Okay? So that's the physical interpretation of these teacher-student vectors. They measure the angles between the different weight vectors. And similar here, there's also a self-overlap of the student, if you will. And if you've ever done replicas, for example, that's another thing that's going to be very familiar to you, right? The self-overlap of your system. Okay. That's the order parameters. That's sort of their physical interpretation. That's what they mean. Now let's see how they evolve, okay? And like I said, let's try to get some ODEs for them. And in fact, let's start with the teacher-student overlap, which is linear in the student weights, okay? And it's actually really easy to get an idea of its dynamics. Let's call this delta R. So this is just because the teacher vector is fixed, right? So this is basically just going to be a teacher vector times the variation of the student vector. And for this, of course, we have an equation of motion, right? That's just the SGD update. So let's put that in. What we'll get is something like this. Okay. Right, so I've just substituted in my gradient descent update. And let's think a little bit about what we're doing here, okay? So this is the change to the teacher-student overlap in one SGD step, okay? So I've drawn, if you will, a new sample x mu, okay? I'm using this to evaluate the gradient. And as you can see, and I've written it all in an almost suggestive way, you can really just dot the equations of the SGD update, right? And then here you get something that's that's a random variable that you already know. That's just the local activation of your teacher, right? In this case, nu m. And what I want to know now is, I want to know what's happening on average, okay? So the whole idea of stochastic gradient descent is that it really approximates the general direction of my gradient. Here the idea is related, but maybe a bit different. I really want to know, since I'm drawing a new sample at every step, what's happening on average here. So I want to take the average here of a new freshly drawn sample x, okay? And if I do this, I realize that I'm left with some kind of integral that looks a little bit like this. This is the error function, right? This is the difference between the teacher and the student output. So let's just expand that. So what I'm left with is two sums. Let's call this L. Okay, minus up. Okay, so I have these two sums, and what appears here is each time the derivative. Okay, that comes from the SGD update. The activation function of a local field, that comes from the output of the student, that goes into the error, and of course this local field here, okay? And now what's nice is with these integrals, again, because my local fields are Gaussian, I can actually, perform these integrals because they're just integrals over Gaussian distributions, okay? The only challenge or the only problem that might arise is you might notice that so far I haven't said anything about the activation functions here, G, right? So now if you want to do this integral, you have, of course, to really put it in a specific form for this activation function, okay? So what Bielen-Riegler and Sarden-Sola looked at was the classic case of the sigmoidal activation function, which I believe was still sort of heavily used also in practice, or at least some approximations to some sigmoidal activation function. And it turns out that for this choice of activation function, you can do these integrals, okay? And so you can write down an analytical formula for them, which will, of course, now be a function of the order parameters, right? It's an integral over a Gaussian distribution, so its result will depend on the second moment. So let's call this result, because it's a three-dimensional integral, I3, okay? And then I don't want to go into too much detail here, but basically you can sort of, they cooked up a clever notation for this, where basically the indices of the random variables are the arguments of these functions. And so that means, once you know the indices, you know which local fields you want to put in, you know how your covariance matrix looks like, and then you can do the integral, right? It's fairly straightforward, but it saves a lot of writing. Minus up. Okay. That's a nice equation because we were able to do the integrals. More importantly, that's a nice equation because, as you can see now, the equations are starting to close. So the update for this teacher-student overlap can be written only in terms of other variables that that other order parameters, right? So it's just vk, and here you will have qrt entering. But so the equation, at least for the teacher-student overlap, closes. Okay, and that's the whole point, right? We want to have a closed form description in low dimensions of this learning process. And at least for the teacher-student overlap, this works. Okay? This is still a discrete update equation. So the last thing, if you want to transform this into an ODE, is you have to find some, you have to go to continuous time. And that's nice because, it's much easier to analyze, at least for physicists, it's much easier to analyze a continuous system that evolves continuously in time than some discrete steps. Some discrete system. And the way you can identify time here is by reminding yourself, okay, I'm going to my thermodynamic limit, right? And so in this thermodynamic limit, the 1 over n basically becomes something like an infinitesimal time step, right? And very neatly here we have a 1 over n factor in front. And you count time basically by counting the number of samples that you've seen, okay? Again, remember we're in this online limit where at each step you draw a new sample from your data distribution to evaluate your gradients. So there's not really a notion of training set, but instead sort of the training samples, they index time. And so you can think about mu of n as a continuous time factor, time variable. Okay? And so in other words, you can show that in the thermodynamic limit as n goes to infinity, this discrete time update equation, it goes to a well-defined ODE, which looks something like this. And I forgot some second layer weights here, I think. Yeah. And here too. Okay, now this is a bit of a hand-wavy argument, I'll admit, and but this was basically the argument that it worked really well. And if you like the more mathematical point of view on this, you can also prove that these ODEs are correct. You can make the statement rigorous, and this is something that we did last year. And just for completeness, let me give you an idea of what that looks like. Because so the technique to show that these things are rigorous, it's actually really neat. It's not too hard to use. It was developed and pioneered in a series of papers that came out from Yulu's group and from Jonathan Mattingly's group at Harvard and at Duke, respectively. Really nice works. And the one that's closest to us probably is the one by Wang. And it's nice because it allows, it's really generally applicable to these kinds of ODE dynamics. So if you write down ODE dynamics for your problem, and you want to prove them, because you want to send them to NeurIPS, for example, have a look at these techniques, and they might help you out. And the statement, or the type of statement that you usually want to prove, looks like this. So you're thinking about the order parameters, R, for example, and you can think about them as a Markov process, right? Because since I'm drawing a new sample at each time step, the next order parameter, it only depends on the order parameters that I have right now, and this new incoming disorder, okay? So you can sort of collect your order parameters in a vector like this. And now sort of to write things a bit more concisely, this is the full matrix QKL at the move step, okay? And the update equations for this Markov process, they're given by your SGD updates that we just wrote down. Okay? So I'll let you run through all these. And then, of course, for all the static teacher-related order parameters, okay, they just stay where they are. So that's very simple. And the sort of informally, the kind of theorem that you can then prove is the following. So you choose a big T, which is bigger than 0, okay? And you then show that for basically all times, which are smaller than big NT, the expectation of this Markov process and this continuous function, I'm going to say in a second where this function comes from, is smaller than some constant that depends on t, but crucially not on n, and it decays as 1 over the square root of n. And m of t is, you might have guessed, the unique solution of your ODEs. Okay? So that's the type of statement that you get. It basically just means that the deviations of your ODEs, it means that the deviation of your Markov process, so for example what you get if you really run this in a computer, will not deviate too much from the ODEs. And this too much, it's a constant times 1 over square root of n. And the way you prove this usually is that you show that the mean of this Markov process equals to your ODEs. That's in a sense what I just did. Okay, you just need to keep the constant. And then sort of slightly trickier part is that you need to show that the variance of this Markov process don't blow up. You start with some fixed initial conditions, that's important. So initially your variance is 0, and then you have to show that sort of on this time scale, the variance of these things doesn't blow up. Okay. And so like I said, you can use methods here from Wang et al., for example. 18, and then we did this for this ODE system in last year. Okay. Are there any questions up to this point? Very nice. You can use the very same techniques and the very same tricks to obviously now define or derive the ODE for the second time dependent order parameter, which is the student-student overlap. Okay. Now, in the interest of time, we're just gonna skip this, and I'll let you read up on this in certain Solar's papers and in Biel and Riegler's, where they explain it really well and really neatly. But yeah, there's nothing new happening. Okay, the only thing that changes maybe is that there's a new type of integral appearing that's now 4-dimensional. Okay, but for F, for example, for the F activation function, you can also do that, and so in the end, you have a fully analytical system of ODEs, and you can now analyze that. Yes. No, they are all ODEs.
But with no detail.
Not even that. So, so that's it. Okay, that's a good point. Where did the stochasticity go? Yes. Right? I mean, I told you about analyzing stochastic gradient descent, right? And half an hour later, I'm talking about these ODEs, which have a unique solution and which don't look noisy at all. They don't have a noise term. Basically, what happens is that in this limit where we are, where the input dimension is very large, the dynamics are noisy, okay? In the sense that the generalization error is a noisy quantity at all times, as are these order parameters, but there's a super strong concentration of measure going on here, okay? And so if you rerun instances of this random process, they will, on this macroscopic level of the order parameters, they will look exactly the same. And so what the ODEs track is basically the mean of this process. And what this theorem tells you is that furthermore, the variance of this process is vanishingly small. Okay. You have to take the expectation. Yeah. You could also ask, for example, what happens if I want to analyze, so okay, there's noise in the stochastic gradient descent anyway because, okay, I'll take a new sample to evaluate the gradient. You could also inject noise, right? You could, for example, say I'm doing noisy or Langevin stochastic gradient descent, so I'm injecting a little bit of white noise or whatever into every gradient update to make it better explore the landscape and that sort of stuff. Now, in this case, this is not such a good idea from an algorithmic point of view because you're doing stochastic gradient descent on the generalization error anyway, so you don't really want to have any disturbances. But okay, just for the sake of argument, say you wanted to analyze this, you will still get ODEs, okay? And basically this sort of, the injected noise, it will just show up here as some constant term that you have to add to your ODEs, and they will change your fixed point. But once you go to this macroscopic level, everything is nice and well behaved and described by ODEs. Does that make sense? Cool. Other questions? Yes?
By the way, I think the conversion to ODEs was also approved by Urban.
Okay. Okay. Oh, that's cool. I'm not aware of that. You should send me the reference.
Okay.
Thanks. Cool stuff. Rüdiger. Okay. Having said that, okay, let's look a little bit at what these dynamics actually look like. Okay? And how we can now extract information from these ODEs, right? So it's very nice. We have something that captures the thing exactly. But okay, you could just run SGD in your computer, and you would get the error curves too. So how can you use these ODEs to really extract some information about this SGD process? So the quantity that you're interested in, of course, is your generalization error as a function of time now, okay? But time is really just a rescaled version of staying steps of SGD. Okay? And so if we, just as an illustration, we're still in this vanilla teacher-student setup, let's focus on a simple case, something like this, where your teacher and your student are matched, have the same number of hidden units, okay? The error curve that you get, very generically, it will look something like this. Okay? And so you can see that there's sort of three phases appearing here. Let's go through them one by one, okay? So the initial phase, or the initial point here, is one where, of course, you started from your initial conditions, so the generalization error is pretty bad. And if you think, for example, about your teacher-student overlap matrix, it will just be 0 everywhere. Okay, because it's just random vectors everywhere, looking in different directions, and in the thermodynamic limit, they will be orthogonal. Your student-student overlap matrix, on the other hand, well, it will probably have zeros on the off-diagonal, because we say we draw the initial conditions IID random. And then, when you start from small initial weights, okay, these vectors will have length that's roughly 0. Let's say we start from slightly larger initial weights, and then this will just be the identity, okay? And as you start training, okay, so this is 0. You start training, there's a first initial phase where the error goes down exponentially, okay? And then you hit this sort of plateau state here. And you get stuck there with an error that's, very suboptimal. This is 0 error. Remind yourself that, again, in this case, the student has enough parameters to match the teacher. They're acting on the same things. There is a global minimum in the landscape, if you will, right? The student could just copy the teacher weights, and then it has 0 generalization error. Okay? But here first, we get to this plateau state. And what happens here is a bit mysterious, but you can understand it if you, again, look at these overlaps, okay, and how they will have changed. And in fact, if we zoom in here, you will find that your overlap matrix here has become all constant, okay? And similarly, your student weight matrix is roughly constants everywhere too. So what's going on? At this point, the student is sort of trying to do the easiest thing, okay? And in a sense, what the student is trying to do, it's trying to fit a linear function to its data. And it's trying to explain the data with a linear function, okay? And so that's doing much better than the initial random guess, okay? But it's still not perfect. Another way to think about this is that I told you, the student and the teacher have the same architecture. So the best way to do would be to copy really the teacher weights to the student. But that's not what the student is really doing here. If you're thinking about what, for example, this row of the teacher-student overlap matrix means, It means that if I'm one of the two student units, right, I have some non-trivial correlations or some non-trivial overlap with both hidden units of the teacher. Okay? And the second hidden unit has also some non-trivial overlap with the teacher, right? So if I sort of draw a little image like this, you know, where this is the student, this is the teacher, I have correlations everywhere. So that's not an optimal solution, right? The optimal solution would be that the students sort of split the work, the student units. Or to use the statistical physics term that was introduced here, is to specialize. And specializing here means that one student node, it really focuses on the output of one of the teacher nodes, okay? Second student nodes does the same for the second teacher node. In a way, they copy their weights, right? And the overlap matrix in such a case for the teacher-student will look very different, right? It will look something like this. That would be much better. And indeed, this specialization transition is what happens when you break away from the plateau, okay? And what gets you here. Now this is a bit magical, right? Because you've never told the student about the fact that, you know, the teacher has two hidden units and, you know, that, you know, you can just split the work like this. But if you train for long enough, this is what happens, okay? And similarly, if you go to the solution, then your student-student overlap will look diagonal like this too, right? That's a really good question. So one really interesting question is, of course, you know, how long is this plateau, right? And it's a bit tricky. In fact, you know, Michael has a whole paper on this where he looked at this numerically in 96. So this is Biel et al. 96, but they basically ask, okay, how long does it take me to specialize, okay? And so there's sort of two things that we need to think about here. One thing is that, okay, this is a saddle point, okay? And the reason you get stuck here is, you know, there are all these permutation symmetries, for example, with how you split up your nodes and everything. So it's sort of hard to break away and find the good direction that takes you off here, okay? That's what's sort of stopping you here. The problem with really giving you a clear quantitative answer is that the length of this plateau, it depends, for example, on a lot of things, including, for example, the initial overlap of the teacher-students, like the initial fluctuations here in the early beginning, right? So it's really subtle because it's basically some noise or a fluctuation that kicks you off this plateau. So it's really hard to give a precise quantitative answer for this tau. But in this paper, they sort of numerically and also analytically look a little bit at how these guys depend, for example, on the scale of the initial fluctuations, the initial weights, and that sort of stuff. So yeah. Yeah. That kick you off here in the end, yeah.
And when you're out, the relaxation is like exponential.
Exactly. So this is drawn on a linear scale, but when you break off, the relaxation is exponential, and you can, for example, like Sutton Solar, for example, calculate the speed at which you go down to 0, and yeah, it's exponential.
This is just in the solution. If you just take the solution of the equations, the differential equations,
Yeah.
then you have to break the symmetry in the beginning to observe this.
Yeah, you want to break the symmetry in the beginning a little bit, and there's there's other ways with which you can play here. So, for example, I took an example that's sort of tough when I said that my teacher's overlap matrix is 1, 1, right? And a way to break the symmetry too would be to say I have teacher vectors which have weight vectors of different length. Okay, so I could have, for example, a teacher overlap matrix that looks like this, or even like this. So there's one dominant direction and one that's a little less important, and that symmetry breaking will really reduce the plateau length too. So it's all about breaking the symmetry here. I think Ruben was first, and then you go.
Yeah. So how does the plateau depend on the size of the two-dimensional?
Really good question. I'm going to come to that in a second. You go. Okay. So that I just drew by convenience. An absolutely equivalent solution would be this. So there's no reason that the first student node specializes to the first teacher node. And you can see that, for example, the formula for the generalization error is permutation symmetric with respect to this sort of reshuffling. Of course, this is only true if for example, the second layer weights are also matched. Okay, but let's think, for example, here for the of a case where we fix the second layer weights of the teacher and the student at 1, which is the committee machine in statistical physics parlance, and then you sort of don't have that complication anymore, and then there's a permutation symmetry, and it really doesn't matter. And where you go, identity or sort of off-diagonal ones, it depends probably on your initial fluctuations too. Okay. So there's this way of thinking about this plateau in terms of specialization, right? And in this teacher-student setup. But initially, remember that I told you that another way to think about it is that at this point here, basically, you have the performance of a linear model. Okay, so you basically have the performance of just doing linear regression. And that's interesting because that's something, first of all, that doesn't just appear in this online setting, but it also appears in the batch case. Okay, so this phenomenology is a bit more general than it might seem at first sight. In the batch case, the way it would appear is, of course, not as a function of training time anymore, but as a function of training set. Okay, so number of samples. Right, so you can think about this as now I give you a fixed data set, and then I let you do something with that fixed data set. I let you do gradient descent on it. I let you crank out message passing algorithms, right? And I ask, okay, what's the final error that you make at the end? And there you also find something, if you will, of an initial decay, and then you hit some kind of plateau. And as you increase data, you manage to specialize. Okay? So as you get more and more samples, at some point you have enough samples to realize that there's actually something that you can do that's better than just this linear regression, and you specialize in your student. And depending on your model and depending on what's the prior on your weights, how your inputs are, this transition can have different looks. And there's a paper from NURBS from 2 years ago, Uba et al., who looked at this in a lot of detail and really looked at the phase transitions in the batch case. So that's really nice. So this specialization is something that we see in the online case, in the batch case. What's maybe even more surprising is that this is also something we see in deep neural networks. Okay? And the way to think about it in deep neural networks is obviously not in terms of specialization to hidden teacher units, because there is no teacher, and how do you specialize in a deep net? Who knows? But in terms of this linear performance of the linear classifier. Okay, and in particular, there was a study last year from Pritram Nakiran and his team. This was in 19, I think. Yeah, which is very nice. And basically, what they asked is, how much of the performance of my deep neural network can I predict if I know how well a linear classifier is going to do? Okay, so on a really high level, on a really high level, the question they asked is, okay, imagine you have a neural network that you train on some data set, okay, and you want to know something about its final test error. And in the beginning, that's going to be a really tough question. But now if I tell you the generalization error that I obtained by training a linear model, how much do you know then about the performance of your deep model? Okay, and they measured this using mutual information. Okay, so the mutual information between the linear classifier and the deep classifier. And what they could show is that indeed there's also something, again as a function of training time, there's an initial phase where a linear classifier and a neural network will do roughly the same in terms of performance, right? So this is performance. And then at some point, the linear model just, can't go any further because it's a very limited model, and then the neural network goes on and on and on. But this, if you will, is also a kind of specialization transition. Okay? So in that sense, this simple phenomenology that we got from looking at ODEs, in the infinite data limit, it also translates to this sort of more up-to-date and state-of-the-art setup.
So here, you see that there is no plateau in the generalization error of the neural network.
So that's a really good question. So exactly. This whole plateau thing in the real neural network where the error really becomes stationary and then you see a drop, I haven't seen too many graphs where people actually show this. There's lots of plateaus that you see in the plots of deep learning models, but what usually happens is that people anneal the learning rate. Right? So they drop the learning rate by a factor 2 or something, and then, but really this plateau in terms of generalization error, that's not something I think that's happening a lot.
But when they draw this picture, it's approximately a picture, or it's something that they can characterize?
I think it was mostly empirical.
Okay, so they just like see that the gradient descent on a linear model is doing the same as the gradient descent on a different network at the beginning, and at some point they diverge.
Yeah, I think that's, that's okay. That's my paraphrase of the paper. I would have to need to look back at it because they had some analytical arguments in some slightly simpler models, I think. But for me, because obviously I knew this phenomenology, so for me what was interesting to see is really that they really demonstrated this split between the linear and the neural network predictor. And of course, they measured this. They had this really nice setup where they measured this in terms of mutual information, and you know better than me how hard it is to estimate mutual informations, right? So my guess is that most of this was in some way experimental. I think Francesco and then Ruben, Hugo.
No, I was thinking that the fact that we don't see plateau in the other neural networks, maybe just because of the data set. Because if you take a data set of images, you have, for example, up-down symmetry is broken.
Yeah.
So by the data set. So and if you take a convolutional neural network where this thing is there, so you have a structure. You don't need to specialize because you can do specialize from the beginning. So, I mean, you don't have to do small fluctuations that put you away from the plateau. You're just out of the plateau at the beginning.
Yeah, I think that's a good way to think about it. Yeah.
Yeah, it's the same, right? The data doesn't have to have uniform weights.
But still, there's much more structure in the sense of, there really is one really strong global attractor in the landscape, right? The teacher weights, and that effect I think is felt. Really, what carries over from here is really not so much the plateau, but specialization in terms of functional differentiations, or this learning functions of increasing complexity. And there's actually, if you look, there's quite a bit of literature. Stefano gave a really nice journal club about this a couple of months ago. There's really quite a few sets of analytical or experimental setups where people have shown that neural networks in some sense of the word learn functions of increasing complexity. They start fitting lower modes of the data first and then higher modes, that sort of stuff. So that's something that we see that, in different setups. And I think that's what carries over here. Not so much really the plateau of the stationary error. Ruben.
So to obtain this behavior, you have a very small learning rate, right?
No, not. I mean, you have a small enough learning rate that you don't just blow off immediately.
Okay, but what happens if you make a bigger learning rate? Do you still see the plateau?
Yeah. So in this noiseless case, so there's no noise in the sense of the teacher output is not noisy, not anything. Okay. If you increase the learning rate, the plateau will shorten. Okay. If you make the learning rate too big, this fixed point here at the end becomes unstable. So you don't learn really well anymore. That's this case of, okay? Now, if you have noise in your system, then you have to be a bit more careful, and then there's a trade-off. Because if you have a bit of noise, in the output of the teacher, for example, your asymptotic test error will be finite, and it will usually depend on the learning rate, okay? And the way to think about this is, if you will, in this online learning setup, if you have noisy outputs, okay, in a sense, this learning rate, it tells you how big is the window over which you're averaging. Okay, if you have a really small learning rate, you make really small changes to your weights for each input that you see, okay? So in a sense, you have a really long window over which you're doing some effective averaging. And if you increase this learning rate, you make bigger and bigger changes for each input, and so, the window over which I'm averaging is getting smaller and smaller, and so the error goes up. But then we're really in a limit where it's almost not so much learning anymore, but more sort of continually measuring a noisy signal. Hugo.
This last part, the user scaling is one where this component is very learned and has a size mechanism.
No, and also, this was really some deep vision, 5-layer convolutional neural network or something like that.
Does that mean that this network begins by saying its last layer, like the linear model in blend,
Ah.
just its first layer?
I don't think you can make a clear. I don't think that the first layers are static initially. I'm not sure, and in particular, I'm not sure about this experiment. But I don't think that necessarily if you train a deep network, it's first sort of the last layers that get trained and then the first. If anything, I think what the intuition that people have is that you might learn the earlier layers first because there's some sort of feature extractors. And then in the end, you only learn the last layers, which are task specific, right? But even that is sort of hand wavy and I would treat with care. Okay? And the time scale here, I'm not quite sure how that scales with depth, for example, or that sort of stuff. But that's an interesting question, actually. Okay. So you see, okay, that's very nice. Let me think if I want to say some more about phenomenology. Okay, so what I propose now for the last half an hour is, there's many more interesting games you can play. Like you can, for example, ask what happens if my student is bigger than my teacher. So I'm over-parameterized in the sense that I can learn more complex functions than the teacher. Okay, and Sard and Solar, when they looked at this, they found interesting effects where the student basically shuts down the superfluous hidden nodes and only uses the correct amount and that sort of stuff. And I'll let you dig into the papers to learn more about this, even though it's very fun. And what I'm going to discuss now is basically how this IID derivation that I just did for the vanilla inputs, if you will, changes if I go to structured inputs. Okay, inputs that come from the hidden manifold model, because after all, we finally want to use the get, right? And then we'll discuss a little bit in the end how to connect how the impact of data structure in this hidden manifold model to, for example, the impact of data structure, say, in two-layer networks or in other models. Okay? Okay, so how do we describe the dynamics now for the same two-layer student, for the same dynamics, so the same SGD updates, but now the inputs coming out of this generator, okay? Now, let's start again with the statics and see what changes there. Now, of course, the sort of initial, the nice geometric intuition that we had in the teacher-student case where there were teacher weights and student weights living in the same vector space, and we could just dot them and look at their angles. It doesn't readily translate to this setup anymore, because now my student lives in R to the n, or at least the first layer of my student lives in R to the n, whereas my teacher lives in R to the c. R to the d. So this guy lives in R to the d, and this guy lives in R to the n. But a good place to start is, again, as you will have guessed now, to think about the local fields, okay? So to think about, for example, the teacher overlap, entre guillemets now, which is still a perfectly well-defined quantity because it's just the covariance between two scalar random variables, right? So I can ask, what is this guy? And again, if I evaluate it, I'll find that it's this sort of matrix product, okay? So it is the student weights and the teacher weights enter, but they are sort of projected, or there's this matrix in the middle, which is the covariance of an input that I put into the generator, okay, and the output of the generator. So it's the sort of latent input correlation matrix, right? So that's the first new object that appears here. And this is a property of the generator, right? So for a fixed generator, this will be a static quantity. All right? Second time-dependent overlap is, of course, our student-student overlap, which again is well-defined, and which is defined, or which you can calculate to to be this, and omega is the second covariance matrix that's going to be important here, and that's the input-input covariance. Okay? That's the covariance of two components in the stuff that my GAN produces. And again, if this is a property of only the generator, right? And so if I fix my generator by choosing its ways randomly or by pre-training it and then using it, these guys are static. Okay, so that's very nice. Now what's a bit less nice is that we have this sum over ij here, so we would like to diagonalize it. And in fact, the whole trick to analyze the ODEs in this particular setup is to rotate into the eigenspace of this covariance matrix and to look at the matrix in this eigenspace. Okay? So in other words, what we're going to say is we're going to diagonalize like this. So rho tau will be the eigenvalues and psi will be the eigenvectors, and we're going to normalize them like n. Okay, and similarly for the sums over I. And then we're going to introduce projections of the student weights, which we're going to call gamma. And we're going to introduce projections of the teacher, okay, which will be omega I k psi to r. And now you should tell me, okay, what's going on? The teacher weights, the teacher weights don't live in the same space as the w's. This doesn't work. Exactly, that's why I wrote omega. So what you need to do first is you need to sort of blow up your teacher weights, if you will, using this phi matrix. That's a little trick. Okay? And then you see that the student-student overlap becomes something like this. And your student overlap becomes something like this. So this is if you want the statics of the problem. Okay? Now I'm missing one thing. And delta is just the relation between the latent dimension and the input dimension, and it's order 1. Okay, so in other words, I'm sending both d and to infinity at the same rate. Okay, so far I've done nothing fancy. I've only rotated things, okay? But there's one interesting insight that you can already get, and that's by looking at the teacher-teacher overlap, okay? So there's one teacher-teacher overlap, which is straightforward as you would expect, just the covariance of the nus and the nu m's, okay? And that's just going to be the product as we had it before, right? Because the C's that enter the nus here are still IID Gaussians, right? Because that's what I feed into my generator. So that goes through just as I had in the beginning on the IID case. And in the vanilla teacher-student setup, this was the only guy that sort of showed up in the dynamics, okay? And you could sort of see how, in a sense, R and Q want to align with this teacher overlap. Now, in the ODEs, there's going to be a second, in this case, there's going to be a second teacher-teacher overlap that appears, okay? And that's going to be, let's say, tilde dt. And that's basically the self-overlap of these projected teacher weights. Okay? It's not a priori clear that this is an interesting order parameter to look at, but if you write down the equations, it's going to come out. And it's going to come out at the place where usually you have the teacher-student overlap in the vanilla case. Okay? Now, why is that interesting? Because if you write this out again more explicitly, I need to make sure that I don't get lost in the indices. No, sorry. Up. So what you basically can see already is that is one way in which this data structure and the fact that the problem is now a bit harder is showing up in the ODEs, right? In the vanilla IID case, I just had these weight vectors show up. Here, I'm basically seeing the teacher, but I'm not seeing it very clearly. Because instead of just seeing the weight overlap of the teacher weights, I see it sort of distorted by this matrix. Okay, and this matrix is again the correlation, where did I write it? The correlation between what I feed into the generator and what I get out from the GAN. So in other words, if my GAN was just a linear function, these guys would be the identity, and I'm good. And I'm seeing the teacher very clearly. But now, the more complicated the GAN becomes, in other words, the harder it becomes to, go back from the X to reconstruct the C's, and so the correlation drops down, the harder it will become to see the teacher-teacher overlap clearly. And so in that sense, the structure in the data and how complicated your GAN is, it really pushes the teacher away from you, and you really just see this very distorted thing in the ODEs. Okay? I find that quite neat, actually. Because that's already visible sort of in the statics. Okay? Now let's think about what the dynamics of these guys look like. So, in a sense, you proceed in a very similar way to what we've just done, okay? So, you proceed first, if you think, for example, about the teacher-student overlap R, so that's a linear quantity, right? These guys, they're static, so the dynamic that I'm interested in for the starter are the dynamics of these projected student weights, okay? And just from the SGD updates and their definition, you can immediately write down the equation of motion, and this is something that should look very familiar to you now. Tau plus and minus the teacher term, okay? No, that's right. Up. Okay, and beta is just a projected version of your input. Projected with the eigenvectors, okay? And then you can proceed in a similar analysis as previously. It gets a bit, so there's some technical sort of glitches that you need to overcome, right? So previously we had the life very simple because we just dotted basically the update equation for W with the teacher weights, and then we immediately had the local fields appearing here, okay? And now you see, now we have to think, and then we know we had Gaussian variables everywhere, and we could just write down the Gaussian average of them, and we are basically done. Now here the problem becomes a bit more work, because what you have here are these two Gaussian variables, okay, which have correlations of order 1, and you have this guy, which is a random variable, which is also correlated with these guys, but the correlation is weaker. It's only 1 over square root of n. And more importantly, the correlation between these guys is not actually an order parameter, right? And as you remember, we want to close equations. So we're happy with evaluating Gaussian averages as long as all the covariances are order parameters, because then we get something, a closed system. So you have to do a bit of work to actually rewrite this in a way such that you get something in terms of order parameters, okay? And I'm going to spare you the details. But what happens in the end is that you get something after a lot of work that looks like this: rho tau times very long function of your order parameters. Okay? And that's really cool. Maybe though not obvious, because okay, that's the good news, right? That's expressible in terms of the order parameters. We're good. We can close the equations. The other good news is that in a sense, so this is the tau component of this projected wave vector, okay, and it only depends on this tau, or on the eigenvalues with respect to rho tau. It doesn't depend, for example, to all the other taus. So in a sense, by diagonalizing the dynamics, here we have something that's local in this space, okay? And this is a hint that we can do a little trick. We can do the following trick. We can rewrite what was previously an order parameter, something like RKM, okay, which in the vanilla teacher student setup was just the product of two vectors. We can rewrite this now as an integral over the spectral density of my covariance matrix, okay, and an order parameter density, if you want, okay. This is just, this is just a way to write this. Maybe what's more clear is if I do this for the student-student overlap, actually, right? Because we saw that the student-student overlap is something like this, right? That was just from rotating the statics, so, what I just pushed away. And we know that if you have a sum like this over these eigenvalues, a good way to think about it is just to rewrite it as an integral over the spectral density of the matrix from which you get these eigenvalues, okay? And then you want to transform this into some sort of density rather than sum, okay? And this density we're going to call a QKL of rho, okay? And QKL, sort of informally, you can think about this as the sum over tau gamma k tau. Here's an indicator function where rho is sort of in this, and delta rho is just a small window. So in other words, we can rewrite these two order parameters in terms of integrals over the spectral density of a density, of an order parameter density, if you will, Q. And what we wrote down here, what we obtained as the ODE, if you will, just becomes the evolution equation for this order parameter density. Okay? And that way we can close the equation in the end. Like I said, I don't want to go through the whole derivation, but sort of on a high level, what's happening is you're replacing your order parameters with order parameter densities. These densities obey an equation that looks a lot like the ODEs. It's got a few more terms, but really, morally it's really related. And you can obtain it using the same techniques that we discussed earlier. And then you still have this integral in the way here. Okay? So that's sort of the price you have to pay for having arbitrary input covariance. Right? So we said that the generator, it shows up, okay, I'll wash it away. But we said that the generator, it can be characterized using these two matrices, the input-input covariance and the input-latent covariance, right? And the two ways in which they show up is for the input-latent covariance to sort of blur the teacher, so you don't really see it anymore. And the input-input covariance shows up by, having to pay this price, having to pay the price of this integral to get to your order parameters, okay? If you want to look at the details, this is in a recent archive preprint with Galen, with Mark, with Lenke, with Florent. And I always forget the full reference. No, I wrote it down, but on which of these very many pages? Okay, it's on the archive. It was published. It was posted there in June. Let me also mention that this is sort of an application of the GET, in the sense that we applied it to solve the dynamics of online learning. Okay. Now I told you on Wednesday that these variables are also important because they also show up in the replica calculation, right? If you introduce your deltas, and in fact, there's a really nice paper of which I have written down the number, and that's this one, Okay, this was work by Federica and by Bruno, who are also postdocs in the group in Paris, and of course Mark, Florent Lenker. And they did the full replica computation for the hidden manifold model. So for the case where the inputs are coming from this one-layer generative model, okay? And they solved it. They looked at the generalization error as a function of various things. They found the double descent. They looked at this in terms of learning from random features and also learning from the hidden manifold model. So if if you're more used to the replica way of doing things and you want to see the get at work, then this is the way to go and a really nice reference. Okay. I think we can call it a day at this point. Okay. Exactly. Or maybe we have 10 minutes to get these open problems ready. Okay, let's do that. Last questions?
Are you sure it's right training this guy? You can use the generator as a teacher and see the generalization error.
So basically using a very complicated teacher, in a sense.
Very complicated student, like the same architecture as a generator.
Yeah. Yeah. So that's one of the things that I've been meaning to do for a year or two maybe, because it's an interesting question. So basically the question is what happens if the student and the teacher become deep, for example, right? Or even pre-trained and that sort of thing. I haven't really looked into that so much, but I know that, for example, a few people have, really in this teacher-student setup. So one reference that immediately comes to mind is by Yuangdong Tian, who's at Facebook. And he's written 1 or 2 papers recently where he basically does exactly that. And for example, one of the questions that he was asking is, do I have specialization, or in what sense do I have specialization? And what he, for example, found for ReLU is that you have sort of specialization of nodes, if the teacher and the student are the same, across layers. So the nodes of your third layer will specialize to the nodes of the third layer of your teacher, something like that. So people have started looking at this, and this is a place to start if you want to look into that. Because that's clearly, okay, if you want to think about open problems and things where we should push this line of research, then clearly depth is one key thing.
This is purely empirical.
There's a lot of empirics here. There's also this overlap thing, for example, that I just told you. He also has a theorem for that. The theorem basically goes like something: if you hit 0 generalization error, then the overlap across layers is positive or something like that. I read this a while ago. This came out maybe last year. But so yeah, people are starting to look into this for ReLU networks in this case. But yeah, clearly depth is one of the directions in which we need to push this. Huh. That's a really good question. I don't see why it wouldn't be possible in theory. I guess it's something you need to do. Well, I mean, it will become a bit nasty, right? Because the weight updates will become a lot more involved than for the simple fully connected case. And so you have to make sure that things still stay, thermodynamic in the sense that you still have these high-dimensional vector products appearing, so that you can close the equations. But it's definitely something we should try. In one dimension, maybe first, and then. Okay, then. Thank you.